Hello again, everybody. I wanted to chat today about house advantage and why it's so important. I'm going to go back to that simple coin flipping game that we discussed earlier. And the idea is I wager $1 and I pick heads. And if I'm right, if the dealer flips a coin and it's heads, I win 75 cents. And if I'm wrong, I lose the dollar. Simple game, simple to understand, simple to gather that the house clearly has an advantage. And if you do the math, you find that the house advantage on that game is 12.5%. So we're going to drill down a bit into that game, actually code the game, simulate the game, and see why the house advantage is so important in terms of driving a player to lose a game that has a house advantage. So I wanted to begin with a little piece of code I wrote, and this is written in Fortran. Some of you may chuckle that I use Fortran, but I have used multiple languages throughout my career, and I seem to gravitate back to Fortran. It's simple. So this actually is the entire program. It's called Coin Flip. I'm going to go through this just briefly. For those of you not familiar with programming, you actually may enjoy this, just to see someone kind of go through what computer software does. And you can see the entire program is maybe 25 lines of code or so. So basically up top here, these first couple of lines are just comments. In Fortran, an exclam means a comment. And so what this program does is you wager 1 unit on a coin flip, pays 0.75 units if you win, and you lose the 1 unit if you're wrong. And this particular program will run 10,000 sessions for a session length that the user inputs. So here, if we skip down to read, that's the way that the Fortran program receives input from a keyboard. So it's going to read a seed, which is used for the random number generator, and a number of coin flips or plays of the coin flip game that you want for each of the sessions. And it's going to run 10,000 of those sessions. So this is what we call a do loop. It's simply a loop that repeats over and over. This particular do loop repeats all the way down to here, and it will go through this loop 10,000 times. Here's a couple variables. Variables are just names for things that I need to know about. So this is a variable that happens to be an array, so it will take a number of different values based on an index. And I'm just setting all these to 0. Down here, I'm actually going to play the game. So I'm going to do another do loop, where now, based on how many times I want to play each session, I'm just going to go ahead and play those out. Here's the actual random number being drawn. It's in Fortran. I'm using a function called ran0, which comes from a book called Numerical Recipes, which a lot of engineers and scientists use. It's an excellent book called Numerical Recipes. I will put a link in the description. And this particular command here will generate a random number drawn in the range of 0 to 2 inclusive. So it's what we call a closed interval in mathematics, between 0 and 2 inclusive. Now what I need to do is take that interval from 0 to 2, which includes decimals and any number you can think of between 0 and 2 inclusive, and I need to map that somehow onto a heads or a tails flip. So the way I do this is I just set another variable, IR, equal to this random number. Now IR in Fortran automatically is an integer, so it will automatically collapse this range of 0 to 2, which can be any real number, to just be 0 or 1, or in very rare cases 2. So I have a check here in this line just for the edge condition of did I happen to get a 2, because I don't want a 2. I just want a 0 or a 1, a heads or a tails. So if I get past this line, then I've succeeded in now I have a head or a tails. I'm going to assume we just bet on heads. So if the random number integer is 0, we win. I will add that to my win counter, and my outcome will be 0.75 units higher. Otherwise, we lose. I will add that to my lose counter, and my outcome, I will have lost the entire wager. And that's it. That's the coin flipping game right here in a nutshell. I have it in a couple of these do loops just to play the number of flips in a session and then play the number of sessions. And then I have some output here at the end just to show what comes out. Just to show you how fast this runs, I can run a version of this real quick. And let's say I wanted to play 10,000 flips per session. And remember, I'm also going to play 10,000 sessions. And you can see that it ends in just a few seconds. And this was 10,000 sessions of 10,000 games. So it's 100 million times I've just played this coin flipping game. And it was done in just a few seconds. Well, the output of that code needs to be brought into something where we can actually see what's going on. And so I just chose to use Excel for that, for this exercise. And let me just bring that up real quick. Okay, here we have the output of that program brought into Excel. And what you can see here is this is the actual output of the program. So for example, this was 100 flips in a session. So each session was then 100 games, and then the simulator ran 10,000 of these sessions. So for example, in session number 5 here, what happened was the player won 52 times, he lost 48 times, ended up with -9 units overall, which is -9%. And so this would be a graph of how the player did for 10,000 sessions of 100 games each of this coin flipping game, based on the simulator. And it's kind of hard to read here at the bottom, but the most likely outcome, as you would expect, where this thing is centered, is on a bin that goes from -13.3% to about -11.6%. And if you remember, the house advantage on this game was 12.5%. So in terms of the player's expectation, in terms of how much the player lost, which is the way this is graphed, we would expect it to peak at -12.5%. And indeed it does. And the other thing to note about this is how wide is this graph? It has what we call a normal distribution, or a Gaussian distribution, sometimes we physicists would call it. And the shape of it is this, what we call a bell curve. And so it's centered on -12.5%, and more or less it goes out over here to about -35%. So that would be like a really bad session. If you ended up here, you would have lost 35% of everything you wagered. On the other hand, you might have got quite lucky in a particular session of 100 games and won. Over here, you might see this is about +10% or so. So it's centered on -12.5%, and it has a fairly wide range, some of which the player is winning as he ends the session. Okay, and that's for a session of 100 games. If we go to 1,000 games and look at that output, we still see that it's centered on -12.5%, as it must be. But what we see is this curve. If you look at the values of the x-axis, it's beginning to collapse. It's beginning to shrink down around that -12.5%. And in particular, if you look here at the edge here, really the player is never winning anymore. So if you play 1,000 games of this coin flipping game, your chance of being ahead is pretty close to zero. There's no positive values here left on the x-axis. If we go to 10,000 flips, then again, it's centered on -12.5%, but we start to see this really collapsing heavily. I mean, these are values around -14.7%, and these values over here, it's hard to see, but they're about -10%. And then if we play 100,000 games in a session, we see that, again, it's centered on -12.5%, but these values over here are now -13% or so, and these values over here are about -11.7%. So if you play 100,000 games of this coin flipping game, you will end up somewhere on this curve. Your probability of where you end up is directly related to the height. So you're most likely to end up at around minus 12.5%. You're going to lose 12.5% of all of your wagers. However, it can be as low as, let's say, minus 13.2%, which is this range. And if you're lucky, which is not really lucky, you're still losing quite a bit of money. You would be at minus 11.6 or a minus 11.7%. So if we were to summarize this, everything we just looked at, if I were to play sessions of 100 games, so I just play this coin flipping game 100 times, my player's expectation would be minus 12.5%. In other words, this curve of distributions is centered right on the theoretical player expectation. And the approximate range is, if I want to count all the points roughly, is about minus 37.5 to about plus 12.5%. So there's a chance I'll end up ahead. And the total width of this range, from minus 37.5% to plus 12.5%, that represents a total width of this range of about 50%. If I play 1,000 games, again, the same player's expectation, the range is now collapsed somewhat. The total width of that range is now only about 16%. If I play 10,000 games, it collapses further. Now, if you notice, it's collapsing right around this minus 12.5. These are always centered on minus 12.5. And from the player's perspective, minus 12.5% means I'm losing 12.5% on average of all of my wagers. The total width here is 5%. And if I were to play a session of 100,000 games, and that would obviously take a long time, you will see that I've pretty much collapsed onto this minus 12.5%. The total width of this entire curve is about 1.6%. So the longer you play a game that has a house advantage, the more sure you will be to collapse around that house advantage. That's what these simulation results suggest, and that's what actually happens in a game. Let me next bring up a couple of slides to highlight theoretically how we could do the same thing that the simulator just did, and to show that these results are consistent, as they should be. So, thinking again in terms of the house advantage, and we're going to stick with this simple coin flipping game for now. The interesting thing is, conceptually, house advantage represents the mathematical benefit by which the casino has the advantage in a wagering game. That's kind of the way to think about it. It's a mathematical benefit. And you can create this benefit either through the rules of play. You might have asymmetric odds of winning a game. So, for example, the red bet in roulette is a game that has the same pay table. If I win, I'll win 1 unit. And if the house wins, they'll win my 1 unit. So the pay table's 1-to-1. But my chance of winning on the red bet is 18 out of 38. So a little bit less than the half. And therefore, the house's chance of winning on the red bet is 20 out of 38, which is more than a half. So that's the house advantage. That would be an example of asymmetric odds of winning. This particular coin flipping game has asymmetric pay table odds. So if I guess heads, I have a 50% chance of winning, and the house has a 50% chance of winning. But if I win, I only win 3/4 of my bet, and if the house wins, they take my bet. So that's an asymmetric pay table, and that's how we can generate a house advantage that way. And of course, when you're designing slot machines or you're designing table games that might have rules where the player can choose how to hit or stand, like in blackjack, you might use a combination of rules of play, asymmetric odds of winning, and asymmetric pay table odds, all folded into a game that might be considerably more complex. But sticking with this simple game for the moment, the expected outcome for any game is simply equal to the summation of a series of each probability of a particular outcome times the outcome. So I here would be an index that goes over all the possibilities in terms of outcomes of the game. And then the house advantage is simply the negative of the expected outcome because the expected outcome is from the player's perspective. So you take the opposite of that from the house's perspective, and you just divide by the wager. And that's how you get the house advantage. So for our coin flipping game, there's a 1/2 chance that we win 75 cents and a 1/2 chance we lose $1. So the expected outcome, if I just plug it into that formula, is it's 0.5 times plus 0.75 units, and then I add to that 0.5 times minus 1 unit, and what I get is minus 0.125. If I take the opposite of that and divide by the wager, which in this case is just 1 unit, I end up with 12.5% as the house advantage, which we knew it was. The simulation told us it was that, and we can, as a thought process, we can talk through that and see how it must be 12.5%. The way to think about that is on average, every 2 flips, I'm going to win 1 and lose 1. So I'm going to win 75 cents. I'm going to lose $1. So for every 2 flips where I've wagered $2, I expect to lose about 25 cents. That would be a house advantage of 12.5%. It all makes sense, as it should. Volatility is another concept in gaming. And conceptually, the way to think about volatility is it represents the scatter of possible outcomes around what you expect theoretically. It's a term of art. In gaming, we speak in terms of volatility, but it's related mathematically to things known as the variance and the standard deviation. Let me present what those formulas are as well. So the variance looks like this. It's again a summation over all possible outcomes where I'm going to multiply the probability of an outcome times the outcome itself minus the expected outcome squared. So variance goes as a sum of a number of terms. It's linear with probability. In other words, the probability term is only raised to the first power. But it goes as the square of the outcome. So if you're wagering 2 units, the outcome would be doubled and the expected outcome would be doubled. And so the variance would go as the square of the number of units you're wagering. The standard deviation is defined as the square root of the variance. And they're both important. Variance is important because it's linear. We can add variances together, just like we can add house advantages together. On the other hand, we cannot add standard deviations together in the standard deviation space. We've got to take a standard deviation into the variance space where we can add them linearly and then take the square root back out. But they're each important in gaming and they're each related to what we call the volatility. So for our coin flipping game, we would plug in to these formulas this way. And we would look at the variance for a single play of the game. What I call variance 1. It would be 1/2 times for an outcome of 0.75, meaning I've won. I then subtract off the expected outcome, which is minus 0.125, square that. And then there's a 1/2 chance that I'm going to lose. So that outcome would be minus 1. And again, I'm going to subtract off the expected outcome, which is minus 0.125. If I plug that into a calculator, I get 0.77. And then I take the square root of that number to get the standard deviation of a single play, and that's 0.88. Okay, so now we've calculated all of the mathematical metrics, if you will, associated with this game. How do we use that to estimate what can happen in a session? Well, first let's think in terms of units, in terms of how much money we've won or lost, or how many wagers we've won or lost. We can use what we just calculated to estimate a session win-loss. The house win, again, this is from the house perspective now in terms of house advantage. We could flip it around and do it from the player's perspective and put in a negative for house advantage, which is equal to the player's expectation. But from the house perspective, the amount of units they expect to win is the house advantage times the wager per play, and let's assume that's constant, 1 unit, let's say, times the number of times you play that game. The standard deviation of that, on the other hand, goes as this SD1 value that we just calculated times the wager times the square root of the number of times you play. And if we want to convert that into percentages, so now we can think more in terms of house advantage and how far away do we expect to end from that. Again, trying to tie this back to the simulation results so that we're comparing apples to apples. We're going to put everything now in percentages. So the house win in terms of a percentage of your total wager is going to be the house win that we calculated earlier, which was just this term. And now we're just going to divide it by the total wager, which is just your wager times the number of times you make that wager. And if you do this math, of course, everything drops out except for the house advantage. So the house win as a percentage of total wager will go as the house advantage. Now the standard deviation of the house win as a percentage of your total wager is a little different. It's this term that we just calculated earlier, again divided by total wager. And what you see is that this goes as some constant divided by the square root of the number of times you play. So as the number of trials n, the number of times you play, the number of wagers you make, that's n. As that gets larger and larger, the percentage of the total wager that the house will win, in other words, that you will lose, approaches the house advantage. And the envelope of possibilities, those shapes that we looked at on those graphs as the output of the simulator, the envelope of possibilities will collapse to this house advantage value, and it will collapse as 1 over the square root of n. In other words, as n gets bigger and bigger, the square root of n is also getting bigger and bigger, and 1 over the square root of n is getting smaller and smaller. So the envelope of possibilities then collapses u onto the house advantage. If we do the math for just one of the examples of the simulator, the example where we simulated a session of 10,000 plays, the standard deviation for that session would then be 0.88, which is what we calculated earlier, divided by the square root of 10,000. That's this formula right here. We plug in 0.88 and we plug in the square root of 10,000 here, and what we get is 0.88%. Now 0.88% represents the standard deviation for the session. And in mathematics, a Gaussian or a normal distribution is well understood. For example, if you take the mean of a normal distribution and you go out plus or minus 1 standard deviation, there's a 68% chance you'll end up somewhere in there. And if you go out plus or minus 2 standard deviations, there's a 95% chance you'll end up somewhere in there. And when we looked at the sim results, remember, we were trying to kind of get all of the points or almost all the points. So it turns out if you go out plus or minus 3 standard deviations, you get 99.7% of all possibilities. And so we're going to use that value because that's pretty close to what we were trying to approximate as when we looked at the sim results. So going out plus or minus 3 standard deviations, we take 0.88% times plus or minus 3, we get plus or minus 2.6%. So the house win for a session of 10,000 plays, the house would expect to win 12.5%. And going out 3 standard deviations, so that's essentially all the possibilities, we would expect it to be 12.5% plus or minus 2.6%. And if you recall from the sim, when we eyeballed that chart, it was 12.5% with a total range of 5%. So it was 12.5% plus or minus 2.5%. Very close to the sim result, as we would expect. I hope this gives you a bit of a flavor for what's going on with house advantage and why it's important, and how the longer you play a game, you'll be driven down to that house advantage. The house will make money off of you the longer you play a game where the house has the advantage. Thank you for watching, and if you have any questions or comments, please include them below. Take care.